Okay, ready to go? How's the homework? Almost there. So what confuses you guys? What's the hardest part?
I'm having a really hard time parsing like the args into like a pipe ready, like a list of args instead, or an array of args.
Mm-hmm. But do you need help with that, or you good?
Maybe I'll figure it out. But then I think it's the hardest part for me.
Oh, I agree. Like, I mean, I was helping the other classmate of yours, and she like, yeah, parsing is the most painful thing here. You know, like IO direction is relatively simple. Everything is relatively simple. Recursion with pipes is a little bit like tricky, right? So, but it's more like something on strings, right? So essentially, the moment you can figure out this recursion, you're good. Any questions?
Yeah, just so I'm clear, when you're doing IO redirection and piping, you can only have a new file in the first pipe chunk, out file in the last pipe chunk, or can they be sprinkled out?
That's a good question, and I was asking myself the same question. I don't know the answer. So what do you think?
It wouldn't make a lot of sense.
Yeah, I agree. So if you have a pipe, then redirecting, like if you have a pipeline or whatever you call it. So it seems that for this first argument, F1, you can redirect input, right? And for this last one, Fn, you can redirect output. I'm not even sure that this is allowed, but maybe someone knows for sure. Does anyone know? Did anyone check? And I mean, it's the rules of this language which is allowed, right? And so it may vary from implementation to implementation. Like roughly speaking, there is no like set language. There is shell which became a standard, but there is a like different versions of the shell which accept slightly different languages as input. I will be okay with this assumption, but maybe we can even relax it a little bit. So let me just quickly let me check what are the inputs on which was check. Not this one. We had multiple versions of the shell homework. Man, and I don't. Tests or something. What? Oh man, we have a ton of tests. Then I give up. Let me. So essentially, what we're trying to figure out is what combinations of those symbols are allowed. But let's set on this answer. Yeah, let's make.
This allows precedence of operators, and the pipeline has a lower precedence.
Say this again. What's your opinion of this?
So the pipeline operator has a lower precedence, and the redirection operator has a higher precedence. So that's how they combine now.
So, but what does it mean to do something like imagine we have F2?
I just tried that on my machine. So the redirection will evaluate.
We'll evaluate first.
Yes, and the pipeline.
Okay, but I mean, this is how you should go about it as well. So imagine we want to do something like cat. Just do something less harmful. Cat readme and we redirected it to WC minus L, right? So that's fine, right? So if I say something like this, that's fine as well. What if I do graph, I don't know, A, for example, one line, right? So that's fine. What if I redirect from split sh? That's fine as well. So apparently shell allows it, this language. But why would that be something meaningful? Like if I write something like DDD here, then WC gets nothing, right? So then probably the correct way is to build it like this. So did everyone get what the question was and what the answer is? Answer is empirical from observing how shell behaves on Unix machines, right? So let's build it this way. So essentially it's allowed, and like your TA says, it has higher precedence. So essentially it's evaluated first, right? But wait, hold on, if it's evaluated first, okay, explain me, how do you want to evaluate this? So because output went to split sh, right? So what is WC minus L takes as an input then? It takes what, command line or what? That's a good question. Okay, let's do this maybe. So okay, does anyone has an opinion? So how would you like to build it?
I mean, I like what we said before, input over here and output over there.
Let's assume this case then. Also, let me take it offline and I think a little bit about it. So maybe I should have thought about it a little earlier. It's just that shell allows this for whatever reason. So there must be some practical reason to do this. My real question now, if we're redirecting here in in DDD, right? So like, what? DDD is empty. Let's do it again. No, DDD is not empty. So it actually, like, it grabbed all the strings. So I'm a little bit confused on what WC is doing in this case. So let's read this shell documentation. Maybe WC just, its inputs are not redirected. So what happens if you do something like WC minus L? It will be waiting for input, right? So, okay, so then its input is closed. That's probably the reason.
I think that's how we evaluate. So we first pass the pipeline. So and set. So the command gets the output of the previous command as its input, and then we evaluate the command inside the pipeline. So and then it replaces its output. So now we are output. So but the command after the pipeline is still taking input from the STD out. So.
No, it's not an STD out, because if you run WC minus L on STD out, it will be waiting for input. So DDD.
It's not STD out. It's still taking the previous output file descriptor from the previous command. But then we change the output descriptor of the previous command. So it's not.
I kind of disagree, because look, WC is not waiting; it returns 0, right? It means that the input was closed. It's essentially like WC minus L. It is waiting for the input from me right now. I am not inputting anything. I say Control D, saying close the input.
Yeah,
so
empty
so
output.
Essentially the WC executes on an empty, on a closed standard input, which is unusual. But fine, maybe there was a reason for that. So let's build it this way then. It's unlikely we're going to evaluate it, but let's build it the right way. So So whoever passes the autograder already, we're not going to change the tests, right? So you will be fine. you're happy. But did you get the discussion here? It's unusual. It's unusual. I was thinking about it the other day as well when I was helping someone. Okay. Any other questions?
There's no hidden tests on the autograder, right?
If you pass them, we're not gonna run them again. I mean, I don't know whether this year we tell you what tests we're running. You probably can easily, you can just print them out because you see the output, right? How you see the output only of the autograder, right? Yeah. But okay, no, there is no trickery. If you pass them, you pass them. Okay, anything else?
So does that mean that the grade that we get on
Yeah.
the autograder will be what we
Yeah.
get?
No, like unless you say, look, your autograder fails, like, and I argue that my grade has to be higher. People typically don't argue about lower grades, right? But we will take it, like we will take a look and review the grade if you ask us. So anything else? All good. Okay, quizzes due on Wednesday. So yeah, please take it. But let's get back. My office hours, by the way, are today, right? So please come if you need help. And today's office hours are tomorrow, and I think the other day is Thursday, right? Or which one? Doesn't even remember.
Wednesday.
Yeah, so Wednesday and Thursday. So please use these opportunities to talk to the TAs. And mine are in person today from 1 to 2. Okay, so let's get back to this, and hopefully, my hope was actually that it will be our last lecture on linking and loading, but we'll see how far we get. So just a quick reminder, we were looking at how executable files are generated and what's inside the containers, which essentially which store them. So essentially, it's an L file with a tiny header at the beginning, which points you to 2 different tables. One table is used by the linker because it shows you where in that file is information which is required to relink the file, or mostly relocate, right? Link and relocate. So find and find symbols, and if needed, move the executable or the object or like the text section and data sections of the file in memory, right? And the second header is second table is essentially table which contains all the sections which you can just essentially loop through and load the program in memory. And if it's correctly linked and ready to run, then it will just, you can load it in memory at this address, it will run, right? So in our question, which I wanted to cover today, like 2 things. What are the static and dynamic libraries? And we'll cover position independent code. So let's think about static libraries. So it's actually very simple on Linux. So a library is just a collection of object files. And you say, look, if I have some number of object files, what I'm going to do with them is just use some kind of an archive tool which just packages them together and keep them together. And so Unix uses this archive tool, which is called AR, right? It's not used today much for anything but this static libraries, but back in the days, that was a tool similar to zip or whatever you're using, tar, right? And this archive tool just supports a collection of any objects. So roughly speaking, what happens is if you have a bunch of like source files and you run them through a GCC compiler, for example, with a -c flag, which stands for compile but not link, right? You'll get an object file for each of them. So printf, random, and then you like just give them as an input to the R tool, and R tool produces a static library, libc.a, right? So conceptually, it's just equivalent to this collection of those files, plus maybe some index which helps you to more efficiently locate the definitions of the functions, right? So because if you're looking for an unresolved symbol, let's say printf, and it's located somewhere in this file, it's faster if you have some kind of a dictionary here which says, okay, it's actually somewhere in this file at this specific position, right? So this is how it works. So like if you use this tool and you say, I have some number of inputs and I just package them together into this library.a as an output, right? then you can take like essentially, if you invoke a GCC compiler again with like having your own main.c function, passing library as an argument, it is equivalent to just essentially enumerating all these files, right? So it's literally just a storage container, right? So that's reasonably easy, and then you will see those flags, like you can say, if this lib class.a is placed in the standard library path, so for example, like user local lib, you can, GCC supports this syntax -l, which says, okay, please, like there is no .a, it will just automatically assume that it's .a or something, and then just like look in that path, right? So that's easy. So just a container. Nothing super interesting is happening here. And as we said, like since linking is a two-pass process, the first linker pass resolves the symbol names into function locations, right? So if you have your main and you call something like printf, and originally the compiler -c will place something like ox, ff, fc or something like, so essentially like looping back on the same symbol. Essentially, you will have in one of those tables, which I keep mentioning, it will say, okay, like the printf is unresolved, and so when you do it, you have to essentially go through all these object files and find the definition of printf, and essentially just patch this address to point to here, right? And just to improve this search, this library formats add an index, which I was mentioning. So it maps names to positions in those files. So again, kind of like a natural idea. We don't have to understand the details, just need to understand the high-level idea of how it works. Okay, static libraries are reasonably simple, right? So nothing like special. I just essentially cover them to make sure that it doesn't remain a mystery for you. The shared libraries are a little bit more involved, right? So they have this .so shared object extension, or DLL, on Windows, right? So let's first talk a little bit, and I was mentioning that before. So motivation for essentially why we need shared libraries, right? So if you do like ps command on your system, like mine, for example, I say, please list everything what's running and count how many processes I have in my system. What will be the answer, you think? How many programs are running on a typical laptop? 100. Yeah, around that. I would say 200 probably, or 380 too. A little bit more. A little surprising, because literally I just running just a couple of handful things, right? But really there is so much running underneath. In my example, I say, like, let's use 1,000. Maybe I was talking about a server machine or something like that. So imagine you're running a system which runs 1,000 programs, right? It means that you're running literally, you need 1,000 copies of printf. If I ask you a question, how big is a printf? What do you think? Like implementation of this function in terms of code section. Make a wild guess.
I guess 300 lines.
300 lines, printf. You haven't used printf enough. Remember, it does all this like f and like whatnot, like quite involved. Like, to be honest, like let's be a little bit more concrete. If we move to the x86 implementation of printf, which is very, very basic. Let's just quickly go here, and we do something like printf, right? So if you do wc-l on this one, you might be close, right? 85 lines, right? But it's very, very basic printf, so which doesn't do much. So just like, it's very restricted. So just like only like these 4 things: a digit, a pointer, or a hex pointer, and a string, right? So, and this is lines. If you do gcc -c on printf .c, oh man, really? Hope for slightly better output. It's warnings. Yeah, who cares, right? So then if we do like size of this printf dot c roughly 1466 bytes, right? So and it's very, very basic printf. So on a real system, maybe we can safely multiply it by 10, right? Okay, so that's problematic, right? So if you're saying, okay, like if you say, I want to think about the disk space and the runtime, right? So last time on my machine, I had 250 programs running, right? And if you say that printf itself takes 5 to 10 kilobytes, right? It means that if you multiply 5 to 10 by 250, you get roughly 1 to 2.5 megabytes of RAM if you just have enough, this many copies of printf. And if you do something like you say, okay, how many programs are there in my user bin directory? Last time I had 2,500 roughly, right? And again, if I multiply 2,500 by 5 to 10,000, it means 10 to 25 megabytes of disk space, or 1 to 2.5 megabytes of DRAM, right? So again, what is that? Today, who cares about 1 to 2.5 megabytes of DRAM, right? So no one cares, except the people who build embedded devices, something like this wristwatches, right, and whatnot, like who really have to care about like very tiny embedded system. Maybe they build vacuums, right? But even like 20 years ago, you know, a typical machine was coming with like 16 megabytes of DRAM, right? And this is a huge amount. And the hard drive was maybe in the order of 100 megabytes, right? And don't even mention what was there like 30 years ago when these systems were developed, right? So they clearly wanted to save space on disk and in memory, right? So an obvious answer is, if you ask yourself, so how can I save it, right? I say, look, I don't want to have 1,000 copies of, or whatever, like 2,000, 2,500 copies of printf on disk, right? I just really want one copy of printf on disk, and possibly, ideally, one copy of printf in DRAM, right? So how can we achieve it, right? So the thing on disk is that we say, if I have this shared library, which sits on disk, I'm not going to link against it. So if I say, if I have a main and I compile it, instead of like linking and essentially like merging these two together, making a main containing a copy of printf, right? I'll just leave them separate, right? So there will be like main and still that copy of printf somewhere on disk, right? And when at loading time, so essentially when they do an exec, the operating system will figure out somehow how to merge them together in memory, right? That seems like an intuitive idea. So just do this last step of merging instead of doing it statically and putting the result back on disk, like I was explaining all this time before. We would do that at the very last moment, right? And alternatively, if you can build your system smart enough, you can make sure that if you run this main and you run this WC and you run maybe ls, right, in memory, they can somehow also refer to the same copy of printf in memory as well, right? So let me illustrate it with a tiny example. So if, again, I use my GCC compiler to compile one of those examples which we use in the class, hello int, I was probably, I mean, I forgot whether I was showing it a couple of days, last week or not, but essentially saying, okay, please, 32-bit code, link statically, and output the binary test, right? It links to 75 kilobytes, right? So it's not a tiny program. And if you do the tricks which I was just explaining, say, please link dynamically, then the output is only like 7 kilobytes, 100 times less. Agree? So that's just because I said, okay, this test will be linked at loading time against other system libraries. Go ahead, question.
Does the compiler not remove unnecessary parts of the library when it's included?
Yeah, that's a great question. So the question is the following. So imagine you have a giant library like print, like, I don't know, libc .so. You're only using maybe printf here. The question is like, do you really need those parts, right? Typically, those optimizations are not done. So typically, the whole thing exists. In case of shared libraries, you never know. Maybe some other program will request this part A, for example, right? When you link statically, it's clearly an opportunity to do those optimizations. And I mean, there's a lot of research literature. It became popular actually when security became a concern, because like there is this idea of return-oriented programming, which abuses parts of your program to do something else. And return-oriented programming depends on the fact that you can find specific pieces of assembly instructions in those parts, which are called gadgets. And I will explain how it worked later this semester. I will explain return-oriented programming. It's actually like, it's amazing. It's so beautiful that when I read these papers for the first time, I thought, okay, it's just impossible. But it's actually possible. And so then people started saying, okay, to reduce the probability of finding those sequences, we will start removing unused parts. Why do you think it's not done typically? Why don't we do these optimizations? Why don't we essentially prune the code, prune the libraries, and throw away everything what is not used? You should probably have enough knowledge to answer. Okay, go ahead. Anyone? Yeah.
Maybe we don't know exactly what is used. We don't know where the entry point for our program could be. We can't exactly prove that whether or not it gets some points of code. We can't say that maybe it's supposed to do that undefined behavior in the department.
You're right. So, but I wanted to, I mean, at a high level, what you're saying is that there is no definite answer for what's used and what's not used. But if I ask you a concrete example, what would be an example where your analysis, imagine you're running some kind of analysis and you say, look, I know the entry point because maybe we can like have this information, but then what? Like, at what point your analysis might get confused?
What if like, you're like, oh, I use this function, but inside that function, points all over the place. You have to go in and die, look at those, and maybe they point at 8 places. And be like, go in and die.
Exactly. So, I mean, you can take two different points of view on this, right? But what your classmate is saying that, for example, languages like C or even unsafe assembly allow you to do anything on the pointers. You can essentially invoke any address. If you know that it will work for you, just do it, right? And some fun, sophisticated language runtimes do it. They are so like intertwined that it's impossible to understand statically what is actually gets called, right? You can say, I can forbid those. I can only allow clean code in my system. Essentially, I can statically essentially run a static analysis at linking time. Static analysis means I look at the binary and I understand what's get called. And even for the function pointers, right? So, okay, typically, like your code will look something like foo, some kind of a label, right? So if you have this code, you're golden. You know that label is a part. There is a couple of problems here because disassembly of the code is not decidable. So it's possible to generate the code which essentially somehow obscures the fact that it jumps out. Like you can jump in the middle of instructions, for example. You can jump in the middle of a move, and middle of a move instruction will be interpreted as a call instruction. Do you know this trick or not? Again, it's widely abused by the attackers. So let me just quickly imagine you have a move instruction, right? So you have an opcode for the move and some arguments, and it's a 5-byte instruction, right? For example, you have another instruction which like jumps through a register, EAX, right? EAX is not statically known because it can be any value at runtime, right? Do you agree with this? Imagine it points here. You don't have a guarantee that the sequence of instructions which is sitting here will not form a call instruction. Maybe if it's even a 5-byte instruction, you will like just spill into the next instruction, right? That's the beauty of x86. That's how unsafe it is. So you jump in the middle of a different instruction, it becomes something else, right? Why do I spend time on this, right? So we'll get back to it, right? It's important to understand that those tricks are possible. That's why I remember when I emphasized a couple of times that Stack pointer can point anywhere in your program. In fact, it can point here as well. And maybe you're unlucky and you can override the code, right? And maybe you can change the move instruction into something else as well. So there are defenses against it, right? But like in general, it's a hard problem. So we'll get to this later. But security became such a pervasive concern that it's part of your life essentially. No matter which job you're going to be doing, you will be evaluated on your knowledge of like basic understanding of vulnerabilities, which is this essentially, the fact that you can exploit the code and do something else with it, right? And so understanding this is important. I don't know if you're taking a separate security class, but we'll cover the basics of it here. Okay, good. Any other questions? So despite the fact that I spent like 5 minutes on that, it's kind of important. Just to warm up for you, like get ready for this. Don't slip. Yeah, any other questions? All good? Okay, so we don't know. Essentially, this optimization is so hard in x86, or like it's impossible without additional restrictions, that it's not done, right? Okay. So if I ask you a question, how to build those shared libraries, right? So at a high level, what you want to do is you want to share the code of a library like printf across all processes in the system, which means that the code section should remain identical, right? Otherwise, there is no sharing, right? If it's a different, then you cannot share. Of course, the data section will be different because each of them will have its own copy of printf. And in one instance, A will be equals to 0, in another, A will be equals to 1, right? So for each of them, we will create its own data section. The observation here is that the data sections are typically tiny because, I mean, we taught you well, and no one programs with a large number of global variables these days, right? Like that's the rule of thumb. Just don't use global variables, right? If you do, something is wrong. And so that's why, you know, the observation is that the text section is big, the data section is relatively tiny, right? Agree? So sharing is allowed. It's easy to do on disk. You say, look, just put this thing in a separate ELF container. Printf will be sitting here with its code and its data sections, right? On disk, easy. As I said, like the moment you load the program, instead of just like, you need some kind of a linker, which does this linking step for you in the operating system kernel, and just merges your main with this printf, resolves the symbols, does relocation if you need, right? And you run. The big question, however, is what happens if this printf is loaded at different addresses in two different processes, right? So now, then what happens? Imagine, I talked about it, so imagine this is printf code section, and this is printf data section, for example. And in one program, it's maybe loaded at address A, so essentially like this. And in another program, it's loaded at address B, right? Remember that if it's a code section, it refers to the data section, it will be some A plus delta. And in this program, it will be the same entry here. Maybe it's a move instruction here, right? It will be B plus delta. Agree? So how will we solve this problem? Clearly, I mean, this is the code section. Code section. We agreed that data sections are different. So it's data 1, and it will be data 2. Because those instances will be different. So maybe it will contain 5 here and 7 here, right? But the code section we want to share. And suddenly, just because it's a move instruction, it needs an address. The addresses are different, right? Everyone understand the problem? So what's the trick? Any design ideas?
Maybe we could have some table that like stores this is where this library is located. And then we can just update our offset so we have A and B just focus on our code and use functions updated.
Yeah, you're almost right. So imagine we have some kind of a table, right? And the table itself will contain the address of this variable, right? However, do we have a guarantee that the table will be at the same address in all the processes, for example? Because you still need to jump somehow load this position in the table, right? So how can we do that? I mean, there are multiple ways actually. Yeah, go ahead.
I'm a little bit confused. Could you like hash the name of the process in the table so that like they can access it from different programs?
Okay, hold on. So the way I'm trying to teach you is that everything is kind of like explained, right? So I don't know if I fail, but let me just draw a better figure here. So imagine just again, just the same, just zoom in on one of these. So you have a code section and you have a data section. Data section is private to you, right? You have a move instruction. Oh, sorry. And it uses an address, like you load, for example, something in the EAX register, but you load from address A, right? This address A is right here, right? In another process, this A will be actually B, right? So you somehow have to consume this, suppress this difference between A and B. What your classmate is suggesting, let's put a table here. And maybe I finally got what you probably suggested, and I will follow up on that. Your classmate says, okay, let's put a table which will contain A in one process and put a table which will contain B in another process, like address of this variable, right, which we're trying to load, which is sitting here, right? Agree? Now the question is like, if we want to do this, we somehow have to find this address C of this entry in a table, right? And make sure that it's identical. So how can we do this? What you're saying is that you said, can we hash somehow? And I don't know what you mean by hash, but can you, for example, have this beginning of the table, like start, readily available to you somewhere, right? And an obvious answer, like, let's just dedicate a register to it. We know that we can, with smart people, we say like, we can build a compiler, which, for example, will use register EBP, for example, to hold the beginning of this table. And then you simply put a number here, like 10, for example. And then you have a logic to resolve like the distance, right, from the beginning of the table to 10, right? That's possible because we say, look, what are we losing? We're losing this the stack frame. EBP is already often used by the stack frame, so we just put this register there, just donated it to keep this table, and we're golden, right? That's a trick. That will work, I argue. It's not ideal because you still donated a register. Maybe there is a better trick. So what would be a better trick?
Make all references relative to the current instruction point.
Exactly, and this is how it's done. So what this suggestion is saying that we can ensure that this distance from the beginning of the table to the current instruction will always be the same in all processes, meaning that we will always load table in front of the code section, right? Why not? Because data has to be different and it will be loaded elsewhere, like anywhere, at some random address. But this we can do, right? And which means that the table will be, again, different for each process, right? So it will be a private instance. This will be shared because what the instruction will contain, it will have a relative distance, and this distance delta will always be the same to that table because the table is like either in front or after or somewhere at the same distance, right? And this is essentially what it gives us. It saves this register because now you say like, if the linker, when it links the program, knows this distance, it will just put it here. So somewhere like move and put some delta, right? Saying, okay, please put the delta. Delta relative, as you said, to what? Instruction pointer. Agree? There is a problem with that on x86 32-bit instruction set. This instruction is not allowed. You cannot use EAP here as an argument. It's not a general register. And x86, for whatever wise insight, we never know, decided that it's not allowed, right? It's still the trick. So I will show you how to 64-bit instruction set fixed it. And they just said, okay, yeah, it's so useful that we'll just allow this instruction. but 32-bit version doesn't allow it. So let's take a look at this, at details. And but at a high level, this is the answer, right? So you will have a table relative to your instruction pointer. So this part which I covering here, this position-independent code, is based on this blog post from Eli Bendersky. I hope it's still online. I have to double check, right? But if like all the details are there, and my examples are from that blog post. So this idea is called position-independent code. The reason I'm covering it is we're not going to be using it in our class unless in your extra credit or something homework assignment which is coming out. But the X6 will not use it, right? It's still very, very useful because every code which you will open on your system, like my Linux system, will have it. And unless you understand what's going on, you will be confused because I explained a bunch, but then you look at the code and it looks different, right? Just because like everything is compiled with this trick, position-independent code. And remember, I was essentially using the flag saying disable position-independent code, so my examples are clear to you, right? So, okay, so at a high level, as we were saying, we want to generate a binary in such a, like a code section of a binary, in such a manner that it doesn't have to be changed if you move it in memory back and forth. So you can put it in any location in memory, meaning that it will become position independent, right? So what can stay unmodified, right? We already know that local jumps and local calls are relative, right? So we've seen it that the call instruction to a function which is somewhere here, foo, in the same binary, we'll use this offset relative to the address of the next instruction. So essentially this address here will be delta from this instruction to foo, right? Remember my example from last time. Similar, the data on the stack is relative to the stack, right? So everything what's allocated on the stack will have something like ESP or EBP here loaded in some kind of a register, right? Agree? So because this is the address on the stack. What we need to typically move is references to global variables, right? And references to imported functions. So essentially, if you call a function which can come from a different library, then you have to put like an absolute address here, right? Because you don't really know where it will be, right? And it's not there. Okay, so here's an example from like previous time. Remember this function which calls like function A from A, pushes the string on this, like which is a global variable. I think, right? So this is a data section, right? So essentially, the function takes a pointer to a string. Function takes one argument, which means that we push one argument on a stack. Sorry, like this is unfixable on this wonderful Wacom. Just touch it slightly and it just draws a line. We push one argument, and this address can change because we can move the data section, right? Similar, if we have, here, if we have a local invocation of a function, we use this relative address, right? So it's A was exactly here inside main, right? Now it's like, I think, linked together. At this point, it becomes in the same binary, so it's a relative address. Like, those things are okay. Let's keep going. So like we already discussed how we can build position-independent code. So essentially, just generate addresses which are relative to your instruction pointer, right? So you kind of add an additional layer of indirection, the table which we just discussed in a class, which will contain information about location of global data and imported functions, right? And we make it to save this registered like EBP, which I said is a possible trick, but better we do a different thing and do not waste a register on that. We load this table in such a manner that the distance between the code and this table remains constant, even if the code is relocated, right? And the linker knows this distance. So roughly speaking, if you have this like move instruction and you have your table here, this distance never changes, right? And so that's no matter like if you move the binary, like if you linked it to load from address 0, you can change those accesses, right? These parts of the address but you never will have to change anything here, right? So let's again take a look at how it can be done. So this table is called a global offset table, right? So your move instruction will use a relative offset, which never changes, into the table. And this entry in the table will, for example, contain an address of the variable, right? So, and the idea is, like, you might ask a question. So if I already have a variable here, why don't I just use this distance? Why do I need like another level of indirection, right? And I think it's actually done this way, but for the variables which are loaded from other libraries, for example, maybe it's a variable inside the printf, this data section is not yet available because the printf will be loaded somewhere else, right, in memory. And it will be a data section of printf. And for those, you need this trick, right? So I think for your local variables, you don't need this trick. So you can refer them relative to your data section, right? Yeah, I think so, right? Okay, any questions about this trick for now?
So does the operating system update the global offset table?
Yeah. So when it loads the program in memory and loads printf somewhere else, the global offset table will be configured to point to correct locations by the loader. So your loader becomes a little bit more complicated. Okay, let's take a look how it can work. Yeah, so GOT is essentially patched by the linker at relocation times, essentially when you load the program in memory. So here I say that each entry in the table contains an absolute address. So this will be an absolute address of the variable. And this is the trick which I was trying to say is problematic. So if you want to essentially, since it's always relative to the current instruction pointer, when I say relative, like we know the distance. Imagine the sequence of code turns into something like take EAP, add the delta, and then load this into some other register, EX, right? That's what we want to do. But we don't have this instruction. We don't have an instruction which uses EAP as an argument, right? Any other general registers are fine. But this one is problematic. So no instruction like this, right? So you don't know where you are currently executing. Is it clear, this problem? So if I ask you again to find a trick to fix it, how would you do this?
Just
Like,
use the PC set function.
Just do what?
PC set function.
What is that?
It's just push the EIP into the stack and populate.
There is no instruction which pushes the EIP into the stack. Like, you cannot do this. That's illegal on x86 32-bit. But there is a trick.
Can we use like a relative jump or call? And jump to that location and then have to come back?
Yeah, so how does it help us?
Because then the relative jump is relative to the IP, so you just provide the distance, the delta,
Mm-hmm.
and then you jump there, and then you have an instruction there that does the jump back.
No, but how did you figure how do you figure your instruction pointer?
If you make the call, then it'll push EIP onto the stack before it jumps to the other function.
Exactly. So instead of this, you do a call of something, like it doesn't matter what you call. But this is specifically, this call instruction pushes EAP on the stack. So it's what you wanted, but through like a loophole. Okay, let's take a look at more details, how we can do this. And as I was saying, this problem exists on 32-bit version, right? So there is no instruction to learn the value of EAP explicitly, but this is the trick which we can use. So for example, one way, you say, call the next instruction, right? Because this label L2 points to the next instruction. So you literally just moving to the next instruction. However, the side effect of this is that your address or address of this instruction, right, which let's say A, is pushed on the stack, right? Your ESP is currently pointing at A. Agree with this? And so you say, well, since I want to just learn it, I will pop it into the EBX register. My ESP will become pointing to whatever it was some foo, which was whatever, before we implemented this call, right? And you learn your value of EAP, right? You agree with this? Okay, so that's kind of cute, right? So you can do this. And so then you essentially build your code like this. You say, look, I will call L2, I will pop the address of this instruction A into the EBX. And if I know the offset, and in this specific example, the offset is FF0, right? So this the distance, right? I will load it into the, I will add it with this learned EAP value, and I will land myself, I will know the address of the beginning of the global offset table, right? Agree? Let's take a look. This example is from the book, so it's a little bit archaic, and I will show you a real example of position-independent code, which you will see, which GCC compiler will generate for you, for example. So here we have a myfunc function, which uses a global variable, myGlobal, right? So instead of just calling the next instruction, they call this specific function which got generated by the compiler called getPCThunk in CIX, I guess. So it lands us here, which means that the value on the stack is actually the value of this address, right now. And what this function is doing, it uses this value, which is on the stack, puts it in the, puts it in the ECX register and returns, right? Why not? It's just a little bit less hacky, right? So calling convention is there. We broke it a little bit, but fine. We didn't break anything. We just returned something in the ECX, right? This is the offset, right? So 1B0, right? We add it with ECX, right? And now we have the address of the global offset table. So what we do here is, okay, we have the address of the global offset table. Now we say, how about we access a specific symbol in the table, right? So we subtract this x10, right, from ECX, load it in the EAX. So that's the entry of this, the entry which contains this myGlobal variable. Currently, it will be saved in the EAX register. Then you load the entry itself, right? So we here doing the load the value of the variable at the address pointed by EAX, and this is the load myGlobal and loaded back in the EAX register, right? And fine, so that's what you did. So essentially, that's myGlobal, and now you add A and B. A and B are allocated on the stack because they are passed as arguments, right? So you add like A and B, maintain the stack frame, pop EBP, and then return from this function, right? So that's a real example. So if you open a program which is compiled by modern compiler toolchain, you will see something similar. So this was taken probably from a couple of years ago. Any questions?
Do you think there's probably more than one functions called getPCThunk with like different names for the register returns it? So I think CX might be the register.
CX is the register, right? So what, like it just that it returns in the CX the address of the global offset table. But what was your question, I missed it, I think.
Do you think there's like a .ex version or .ex?
I honestly don't know. I would guess that it's possible. So probably here, the reason they use this version, I'm guessing, I don't know the answer for real. I'm guessing that this register ECX is not used and it's okay to pollute it, right? Remember, I think ECX is a caller safe register, I'm guessing again. So the function says, okay, I don't care what the value is in the ECX, I'll just use it. And if the caller needs it, it will have to save and restore it, right? And so that's why it's convenient. If you're in slightly different code sequence, you might say, well, I already have something in the CX maybe, but nothing in some other register, so let's use another register. So I would assume that that's the nature of this trick, but I don't really know. Any other questions? Do we understand how it works, this position-independent code, right? Okay. Do we agree that if we move this code up and down in memory, we don't have any symbols which we have to relocate? Because like the offset of the table is this, right? It's the distance from this instruction, roughly speaking, to the global offset table, right? And so if the distance is always preserved, then we are fine, right? Okay, good. What about function calls? So this example was covering the global variables. What about function calls? Can we do the same trick? We can, but what can go wrong, or what is not ideal if we do the same trick? Ten more minutes. I know the answer.
Is it really expensive to do this every day?
It's expensive, but why?
Because we have to load it in position and add some stuff and change some stuff every time.
Kind of. I mean, your intuition is correct, but let's take a look at some details. So the same approach can work, right? But unfortunately, it's not done. What is done instead of called is called a late binding. In most cases, you can do early binding, but it doesn't make sense in most cases. So when a shared library refers to some function, the real address of that function is not known, right? So resolving this address, similar to how we resolved like the address of this global variable, is called binding, right? The problem is following. So in many libraries, most routines are never called. So for example, libc has over 600 routines, but and this is way more than the number of, maybe 10x more than the number of global variables. Again, because we know that we should program with functions due to modularity, split long pieces of code into functions, right? But we say, let's avoid the global variables, which means that, okay, we have only a few of them, right? And when we resolve those addresses statically, when we link the program, it's fine because the binding is done offline, right? So there's no runtime cost. But when we load the program in memory and we load the version of a printf in memory, it might take some considerable amount of time. Remember, I told you that linking something like a Linux kernel takes forever, right? Because it, like a lot of linking. Imagine we start something like OpenOffice, for example. Again, it's a large program, tons of libraries. It will take a considerable amount of time to resolve all the entries, and you will see the difference, or you will feel it as a human. That's why they say, okay, let's not do this. Let's just leave it as is. Essentially, the addresses are unpatched, right? And then when the function is actually used, we'll use this lazy approach. Only when it's used, we will resolve the errors of a function, right? So essentially, at this point, it's kind of magical, right? So the linker is baked into the program, the thing which resolves the errors, and it will be running concurrently with your program on demand. So let me show you an example. So this is the idea which is called procedure linkage table, PLT. So imagine you have a function. What you do, you compile the code in such a manner that the function uses a relative offset to land on a specific entry in this PLT table. It's function number n, right? So what happens here, you essentially say, okay, I will read from global offset table an address, and I will jump to something here. And this address is originally configured to essentially jump to a magical location here, which says, please call the function which will resolve this unresolved entry. The second time we will call it, this address will really land us on a function, like on a foo, for example. But the first time we will essentially land back. This is part of the linker, which essentially figures out which function you're trying to call and patches this address, right? So again, you might see it in practice. When you're debugging a complicated program on Linux, you see, wow, like I really like single-stepping assembly instructions, and you suddenly land on some part of the linker here. And it's because the symbol was not resolved. Essentially, the first time you invoke it, it will take much longer because this thing will do the resolution, figure out where the foo function is in memory, and will patch this address, right? So this is called this lazy linking with this procedure linkage table. So again, POT is part of the executable text section, so it doesn't need to be changed because everything is kind of baked here together. This is all read-only, but this is the only writable variable here. As I was saying, each POT entry is a short chunk of executable code, has a corresponding entry in the GOT, contains the actual offset, right? So, and it's resolved after the first invocation. Let's skip here. This is like the first invocation, right? Lands you back on the resolver. Resolver patches the entry, and the second invocation will be essentially landing on a function itself, right? Okay, so and if I give you an example, so you have this ML util func here. You call it, use the same kind of thunk. This one uses bx, right? So we know what we get out of it, right? So we get, it resolves the address of global offset table. It first lands the IP saved in the EBX. So this is here, right? No, we actually, I don't have it. It's a different thing. So this one inside it, similar thunk. We used CX in the first example. This one uses EBX, right? And then adds offset of EBX. This is the offset to make sure that we know where the GOT is. And this is a specific entry in global offset table, right? So what we do next is essentially we push the arguments. So this is the argument A to this function. We push it on a stack, right? So our, what are we calling? This is a little bit unusual. So essentially what we're doing here, this argument A is our local argument. So we save it in the EAX register and then push EAX on the stack, right? And then we call this entry in the PLT, right? So this entry in the PLT, what it says, okay, I will jump to the address, specify it in the GOT. So right now, it's EBX plus 14 contains the address in the specific invocation, contains the address of this resolver, right? So, which is, in this example, is really just a fall through to the next instruction, right? Because this is why I mentioned it here, that this is exactly how it's configured. So it just falls through to the next instruction. We prepare arguments for the resolver, saying like, okay, like x10 is the argument we want, is the function name we want to resolve. It's entry 16, right? We jump to this resolver. Resolver essentially returns, patches the entry, and like after the first invocation, this will specifically go to this function. So essentially this EBX plus x14, because remember EBX contains this is how we configure it. That's the entry in the GOT, which contains the address of a function, right? So this will land us here next time, right? So that's essentially how the compiler will generate this position independent code today. Any questions? Tiring, but useful in practice later on in life when you really will see this code. Again, so I think it will be easier for you when you see it in practice. You'll at least understand, okay, yes, I remember that was covered in the lecture. So we'll come back and say, okay, like I got it, right? So it's, I don't think we're going to use this concept in this class, right? Explicitly, it's more for like, I might ask some questions about it, but not much. But I still argue to read this, the blog post, which I'm essentially referring to. So, okay, no questions. Everyone is clear. Just another layer of indirection. So again, what did we gain? So processes can share code because the text section of a program is the same, or the library is the same in each instance of a process, like it's read-only plus executable, right? Each will have a private global offset table, right? So those will have private things, but this is much smaller than the text section, right? So it's okay to waste a couple, 1 or 2 pages on the GOT, but still share like those, how many, like 15 kilobytes of printf, right? And with the POT, like since GOT, like this will be addresses of the function and like instances of a global variable and functions, like addresses to what needs to be called. And since GOT is already private, our POT trick allows us to essentially save the linking time, right? So essentially, when you load the program, you don't link anything, and then you link lazily. Okay, let's just spend 2 minutes. So what do you think are advantages and disadvantages of position-independent code? Otherwise, I will come back to it next time. What is the disadvantage? We already know advantages we can share. Why is it bad for you? It's hard to try to debug. Not really. I think you'll be fine after looking at it for the first time.
It will have a much larger overhead on the loading.
Correct. But on what?
On the loading time.
Loading is actually fine. And with POT, the loading time is reasonably fast because you don't link much. But it adds overhead because on function invocation, because a typical function invocation is a call which pushes something on a stack. So let's say it takes 2 to 3 cycles. If you have additional arguments which you pushed here, each of those will take, let's say, 2 cycles as well. So the total invocation time is like 6 to 7 cycles. Not ideal. That's why we do function inlining, right? But not super bad. But with POT, you first call the thunk, return from a thunk, save something, access another table. It kind of adds up, right? So if you're really cautious about what is like my running time, again, matters, high frequency trading, genomics, because you just do it so many times, then you have to avoid it, right? What else? I think that's the main disadvantage, to be honest. So you have to be careful, right? So the code gets slower. You also pollute one register because you have to keep the GOT pointer, right? So x86 has only 7 registers free because EBP is already taken. Oh, hold on, like ESP is taken, EBP can be taken as well. So maybe you can have only 6. Losing 1 is bad. Like on 64-bit version is less of a pressure, right? But essentially, yeah, you have one more memory dereference, one more code to find GOT. So just be aware that those are the costs. So when someone tells position-independent code, you say, well, it runs. Good, you share a memory. Another thing which I didn't mention, it allows you to randomize your address space, which will complicate life for the attacker. Because the attacker says, I don't really know a priori where the printf library is, because the operating system might on purpose place it in different locations unpredictably at random values to make sure that the attacker cannot jump to an entry in this library, right? Unfortunately, this is easily kind of discoverable. There are techniques to like essentially break address space randomization. But nevertheless, it's used all the time. So every code which you will see on your machine will be compiled with this WSPIC, just because the sharing benefits are so large. Okay, let me stop here and we'll quickly finish. I'll talk about what starts before main very, very briefly next time, and then we will move on, right? And I will try to remind you next time what is it we're doing in this class. We start booting operating systems finally, which is fun. Okay, thank you. See you Thursday.
So I think in the